All right, guys, I'm going to go ahead and get started. So, yeah, there's that. My name is Eric Lubow. I'm the CTO of SimpleReach, and I'm going to talk to you today a little bit about how we built our architecture to process the amount of data that we see. So, these are the things I'm going to talk to you about. I'm going to tell you a little bit about the company. I'm going to talk to you about what the goals of having that architecture are, what the tools that we use to build them are, and then I'm going to hopefully have time for some questions, but there's no guarantee there. So first off, one of the things that we learned when we were starting to work with really large amounts of data is that most of it's absolutely useless. And you have to get through the useless stuff in order to get to the good stuff. But the actual way to phrase that, which I prefer a little bit more to Borat, is this. Even with the right tools, 80% of the work of building a big data system is acquiring and refining the raw data into usable data. So before I show you how we do that, I want to talk to you a little bit about what SimpleReach does. And this is the shameless pitch part. So what we do is we give content creators the ability to track engagement at a social level. And what that means is all these folks who create lots of content, guys like Forbes, People, Time, they publish hundreds, sometimes thousands of articles every day, and we give them the ability from the instant an article is published to track all the social actions and social engagement in real time across the entire web. And we present it to them in this beautiful dashboard. So what are some of our stats that entitle us to say that we're a big data company? Well, we look at millions of URLs every day. We look at about 1.25 billion page views per month, and that grows pretty much every day. And we look at about 500 million events per day, which translates to about 6,000 events per second. Again, that's growing all the time. We're on EC2. We're on Amazon. We use Amazon Web Services very heavily. And we auto-scale anywhere between 125 and even now it's a little out of date, to up to about 180 machines every day, just depending on the traffic peaks and valleys that we see. And what we did as a company was we built a predictive measurement algorithm for the social web. Okay, so how did we do it? We use all of those. We use all those technologies in order to be able to deliver to our customers and internally deliver to the team all the data that they need in a timely fashion and present it to them in the fashion that they need. We use Vertica, Redis, Mongo, Cassandra, Solr, and in terms of programming languages, we use Ruby, Ember.js, Node, Python, and Go. And you'll notice Java's not on there, and I'm super thrilled about that. So in order to build this system to process all this data, we have a couple of goals in mind. We want consistent non-data storage layer access patterns, and I'll show you what that means in a little bit. We want data accuracy across storage engines. If you're storing the same data in Mongo as you are in Cassandra, you want to make sure that the numbers match. There's really interesting ways that it appears when they don't. You want to minimize downtime or minimize the cost of downtime, because there will invariably be downtime, so you want to minimize its impact. You want highly available systems. You want to allow access to many tool sets, right? If you're using all these systems, and if you're using Mongo, you're using Cassandra, you want the access to the toolkits and the tool sets that each one of those systems will provide you, because certain things there's just cool tools for Mongo. There's just some cool tools that only work on Cassandra. There's just some cool tools that are only backed by Redis. So you want to be able to take advantage of all those things. All clients that need to talk to your architecture, and that's not people clients, that's consumers of data with algorithmic clients, system type clients. You want them to have minimal knowledge of the underlying architecture. You don't want them to have to know that they have to talk to Mongo under the hood, or that they're talking to Mongo under the hood, or Redis under the hood, or Vertica under the hood. You want them to be able to just ask their question, find the data that they want, and get it back in a consistent manner. You want authentication, tracking, and throttling. And I will show you why that's important in a minute. And you want to control your data flow patterns. These are the tenets that were very important to us. So consistent data access patterns. For us, we have something called the real-time score. Cassandra gets stored as a composite column. In Mongo, it can either be stored as real-time, score real-time, or SRT, depending on whether or not it's a short document or a long document. So rather than having the client ask for which one's which, you just have a consistent access pattern. Always call it real-time score. So one is good, one is bad. And this will become important later on. So why is authentication, tracking, and throttling important? Well, it's really easy to have services run amok. When you're deploying all the time different consumers, different data producers, you're ingesting different types of events, it's really easy to have these things just over-process, ask too many questions, or you can just end up writing some bad code, and not that anyone here writes bad code, but just in case someone did, the services could just DOS yourselves internally. So you want per service access keys. So every single one of our services has their own internal access key. You want to track call volume because you need to know, do I need more API endpoints? Do I need more capacity to handle certain types of requests? Do I need more capacity in the data storage layer for this type of request than, say, another request? Again, you want to prevent internal denial of service attacks. These are unintentional, but they can happen, and when they do happen, it really sucks to blame yourself. And you also want to monitor availability and performance of those calls. If you typically see that, say, your call for an account data, for a bit of account data, takes 10 milliseconds, and all of a sudden it's taking 40, well, that's, it might only be 30 millisecond difference, but that's kind of a big deal. So how do we control our data flow? We use something called NSQ, and I'll show you what NSQ is on the next slide. But for us, NSQ is a really interesting piece of software because it allows a couple of things. One, it allows us to queue up all of our requests, all of our events, and all of our to-dos at every stage. And it allows us to do multicasting of those requests. So, for instance, say a new tweet comes in. It gets stuck at the edge. So our social data consumer will pick that up, and we'll multicast it to 3 different consumers. It'll first pick up the batch and write data, right? It'll just take a whole bunch of tweets, put them together, and process them, update a total count, and write it to disk. This way you're not doing one write for every tweet. You can group them up, and in Cassandra, you get to take advantage of like the batch mutate, for instance. Raw data, same thing. You just take the raw data, put it in a batch mutate, and have Cassandra write it. This way you turn many writes into one write. And on our end, we do something where every time we see a social event, we like to calculate a new score, because that obviously updates the value of a particular piece of content if it was tweeted about. So we then update the score, which then will create a new NSQ job for writing the score to the various data stores that it needs to go to. So at any point, we can control the flow of that data, and we can say, stop here while we adjust one piece, and then continue to pass it along. So what is NSQ? NSQ is, as you can guess by that little introduction, is a queuing system that was written by the good folks over at Bitly. And why do we like it? Well, it allows it's distributed and decentralized, meaning that anytime you add a new message producer, you can have the consumers, which are also decentralized and can be anywhere, find out about that consumer through a lookup daemon. Find out about the producer through a lookup daemon. There's always at least one message, the guaranteed delivery of a message will happen at least once or more if you want multicast delivery, which is, again, something we make heavy use of. There's that. Runtime discovery I just talked about. Every time you add a new consumer or a new producer, the lookup daemon will tell the consumers or producers where they need to look to get more messages or to get the existing message sets. The controlled data flow allows us to create maintenance windows with no downtime. So, for example, where we were writing that raw data, we can just let the queues back up while we, say, do a Cassandra upgrade, run through all of the upgrade nodes, and then let that stuff process. And the processing will be quickly because we're not writing single events. We're batching them up into groups of, say, 100 or 1,000 and letting them write in groups. It also has a really cool feature where it's just ephemeral channels. So if you want to just take a look at what's coming down those message queues, you can look at it, and you won't lose those messages. It won't act them, and you can take a look at what's going on, and those messages can get processed by your actual system, and you don't have to worry about the delivery. So what does that look like when it comes to our actual system? We have a bunch of different ways that we collect data. The specifics are not really important, but from the internet, we make sure that all data does what we like to call flowing downhill. So if it comes from the internet to our edge collectors, hits a set of queues, those queues talk to the consumers, pull from the queues. The consumers will then go to the internal service architecture to get any data that they need to process their jobs. That internal service architecture is responsible for talking to the individual data storage layers and then passing the information back up, and then it will write them again going downhill. And I'll show you what the internal service architecture looks like in a minute. So how did we get here? I'll tell you, it was with making a lot of mistakes. A lot of mistakes, a lot more than I'm happy to admit about. But the biggest thing that we needed to figure out was we need to understand what our access patterns look like. And that was everything from how often we access each type of data store, the types of messages we produce, the types of messages that come in. Everything revolved around knowing where we could be accepting of read latency and knowing where we could be accepting of write latency and knowing where the real-time patterns were important and knowing where the sort of offline jobs would be important. We built the service-oriented architecture, and we also had to do a lot of data accuracy checks. So again, if you have data stored in Mongo and in Cassandra and in Vertica, like in our case, and actually Redis as well, if those things are not all identical, then when you pull from one and you pull from another and they don't match, and you can show them both on the same page, for instance, then a customer is going to look at that and be like, well, how come this thing says 20 tweets and this thing says 25? There's clearly a discrepancy. So one of the things that we had to build is going down through the line, all the consumers needed to be aware of what was being written to the other data stores so that we could ensure accuracy in one data store versus the other data store. And we built a framework out for testing for testing different engines. So what this means is that as in front of the service architecture, the service architecture sits in front of all the data stores. So as we were trying to decide which data store was going to be best for a particular feature or feature set, we needed to see, did we want to use, for instance, Vertica? Did we want to use Vertica? Did we want to use InfoBright? Did we want to use InfiniDB? All these are column storage engines, and for us to find the right one that fit our business and fit those features, we had to figure out a way to do it. So what we were able to do was just plug and play. We put all the storage engines behind that service architecture. We ran the query against the service architecture. The architecture would then say, okay, I know I need to run this query against Vertica and InfiniDB and InfoBright. The results should all be identical. It'll log the response times, write them off to a different place for us to look at later. And when we decided which one we wanted to go with, which was ultimately Vertica, we just pulled InfiniDB and InfoBright out. Zero downtime. Nobody was the wiser. We made our decision, and we had an entire testing system. And we can do the same thing with queuing engines if we wanted to try Rescue versus NSQ or RabbitMQ, because that service architecture gives us the ability to have a consistent access pattern and put space and time in front of requests. The other thing that we did that gave us the ability to build this architecture out is we made sure everything looked the same every chance we get. So the base image starts out with an Amazon AMI. We have our organizational information, which, as you can see, is users, is the application-specific configuration. Application groups, meaning does Mongo S need to be on there for Mongo sharding? Does the NSQD client need to be on there for consuming or for producing? Or if it's a lookup. And then we have whatever application sits on top. And this provided us the ability to say, anytime we need to launch a new image, we just launch that base image, we put the organizational specific stuff on there, and then beyond that, we decide what application group does it fit in. Is it a database? Is it an application? Is it a web server? And we put the appropriate things on there. So what you're looking at here is the basics of a producer and the basics of a consumer. So this is very pertinent to our messaging system. This is all because we have a great systems guy. I'd love to say team, but we're a small company, so it's really just one guy with a lot of headaches. And I can't get him to wear the hat, so I've tried. So we make extensive use of AWS. AWS has some great stuff like OpsWorks, which is a chef-based system for configuring machines and application types. We also monitor everything very heavily. And anybody who's had any level of monitoring experience know that no matter how much you do, it never seems to be enough. So we've got Nagios for the base monitoring, StatsD for application-specific instrumentation, and I would love a replacement for Graphite, so if anybody knows one, please tell me, because it's not as awesome as we'd like it to be. So again, Chef, OpsWorks, Vagrant, for anybody who does systems in the room, it allows you to spin up a small machine setup on your local machine, so you can have a production-like scenario, or production-like setup on your local for development. CSSHX is a cluster SSH client, which basically what we used before we had the ability to use Chef and deploy across everything. We would just spin up cluster SSH sessions, SSH into 100 machines at a time, run the command, and then close that out. That is exactly as painful as you would imagine. Deployments, we do now with Chef. We migrated from Capistrano. But again, having a consistent deployment system was very important for us to be able to get to the point where we are today. Again, documentation like monitoring, no matter how much you have, it's never enough, but it's very important in order to convey from the system side to the development side how to both monitor and instrument and do all the things that are really important for everybody to understand how well your system is, or more than likely is not working. So I put this slide up here because if anybody is working in AWS, they typically stick to the standard, the EC2 and EBS volumes. And that's good if you're a small shop, but it's also not good. And the reason it's not good is because there's all these other features that make your life significantly easier, and we were kind of hesitant to use some of them. Putting our Vertica cluster inside of the virtual private cloud meant we were able to reduce latency between machines. Understanding what external tools are available. So for instance, we run a lot of offline jobs. We run a lot of MapReduce stuff. And Elastic MapReduce is good, but you have to have everything on S3. So what we did to get around that was we found a company called Mortar Data, which uses Elastic MapReduce under the hood. You give them access to some of your S3 buckets and even other methods of access, and you get to take advantage of the AWS services without even having to understand EMR. Elastic Beanstalk, every time we're doing new Rails development or testing new apps, we just spin up an Elastic Beanstalk app, which basically comes with all the Rails pieces built in, and it's so much less work for us to do on the system side. So all these things are tool sets that we get to take advantage of because it can just plug and play right into our architecture, and the developers do not need to become aware of additional things in the architecture. So this is actually what it looks like in a very superficial sense. I promise there's more than that number of machines, though. So what does the service architecture look like? Again, we start with our base image layout. I can't stress how important having that base image layout is, especially when it comes to the monitoring and instrumentation. So the proxy machine, and you'll see on the next slide what the proxy machines are for. The proxy machine sits in front of any storage machine and it tells the requesting app to hold on a second while it gets the information. So the proxy machine is, for instance, 10-minute content or hourly content. And the reason that these are important is because every time the request comes in, it's up to the endpoint to decide where, in order to keep the information from the people requesting it or the system requesting it, it provides that proxy layer so that the 10-minute or hourly content says, hey, I know I need to get this type of data from Mongo, this type of data from Vertica, and this type of data from Cassandra, and packages it all up and sends it back through JSON, in a JSON format back through to the querying machines. The reason that this is a very good methodology is because it does not force the existence of a giant monolithic service architecture. So every time you do a code deploy, for instance, if somebody makes a typo and it takes down your entire internal service architecture, that's, for obvious reasons, a problem. So what we did was we broke it all down into little chunks. So each API endpoint is its own tiny system. So 10-minute content, its own little Python app. Hourly content, its own little Python app. Accounts, its own little Python app. So, and it's not just Python. Python is the example. We use whatever language is actually best for the data storage layer. So in some cases we use Go, in some cases we use Python, and in some cases we use Node.js. So we did this for availability. We did it again for the consistent access patterns, which is another feature that I can't stress enough. Again, minimal downtime on your changes. If you want to deploy just a change to, say, one endpoint, there's no need to deploy a giant, again, monolithic service architecture war file or whatever it might be. You just deploy that one little app change, restart that one app. It becomes unavailable for, however long it takes to restart that app. And if it's a small one, it'll probably take a second, maybe, if that. And you've got yourself a newer version of the endpoint. Smaller code deploys. Clearly, I like that word. So how do we keep ourselves available? We made sure that even though we spin up and auto-scale quite frequently, we made sure that the distribution within Amazon, at least US East, is such that we can lose an entire data center, like US East 1A could just drop out of existence, and we'll still be good. Because every time a new machine comes up, it checks the other availability zones to make sure that we're doing some evenly balanced machine deployments. And here's an interesting fact that we learned the hard way last week. If there is not an even number of machines within an availability zone, elastic load balancers will push more of a disproportionate amount of your traffic into the availability zones with more instances. So for instance, if we have 4 instances of an endpoint in US East 1A, 4 in 1B, and 3 in 1E, then 1E will get like 10% of the traffic, and the other 90% will be distributed between 1A and 1B. If you add one more instance, equally distributed. That might not seem like a big deal, but when you've got millions of events, it's pretty easy to take down a small number of machines. Hence that internal denial of service attack, accident stuff. So you're always going to run into problems. And anybody who's seen any of my talks, I just love this unicorn, so I put them in everything. It really has no meaning, but you're always going to end up with problems. And this guy clearly has them. So the reason we built that architecture the way we did is because we've seen, when we've been in a scenario where US East 1A, for instance, has gone down, and we haven't. So in fact, when I was creating this slide, I guess about 6 months ago, prior to another conference, US East 1A did go down, which is why I actually used this one in particular. And we did not go down with it because of our distribution. Every time we want to create a new service, we have a very specific subset of questions that we have to ask. And we ask ourselves the same set of questions along with a few others. First, can the host of the service be completely homogeneous? Meaning, does it fit with our pattern? Does it fit with that architecture pattern of the chef base, the organizational users, and then the application? Or the application group, and then the application itself. Can it accept downtime? And what does downtime look like? Can you create a scenario where you can let the producing of messages back up in a queue with minimal impact? Because that's always our goal, is to have the minimal amount of impact for downtime. Does it fit into an existing service? In other words, would it be better to lump it in with another service? Would it create a large code base for that service, or does it really need to be its own? Does it require data center distribution? The answer to that is almost always yes. But again, you just have to ask because you need to know what trade-offs you may need to make when creating a new service. How should it be instrumented or monitored? And again, this is also very critical because, as I said, denial of service attacks, whether internal or external, you're going to want to be aware of them, and you're going to want to know what normal usage patterns look like. So, just to tell you everything that I already told you again, only in a few short bullet points, you need to know what you're looking at. You need to know what you're working with. And that's sort of an evolution. We made a ton of mistakes over the past few years to get here. We're quite happy with where we're at, but we're still working towards smaller, more efficient code bases and deployments. So build, use, and integrate the external tools. Again, NSQ ended up being a great tool for us. And the ability to test and easily integrate new tools also ended up being one of the most valuable things that the service architecture allowed us to do. Abstraction, creating good ways of having your querying programs talk to your consuming programs. So the language that is used within programs is actually very important. Homogeneous distribution, again, that's architecture and that's individual machines. And monitoring and automation. So those are the big things that really need to be thought about. This is the new thank you slide. I've decided that. So if any of this sounds even remotely interesting, feel free to come find me. Last thing I have is just a little announcement. Myself and this gentleman right here are writing a Cassandra book, which is hopefully going to be published in September, called Practical Cassandra. So be on the lookout for it. If you have any questions, I got 2 or 3 minutes, so I can probably take a few.
So the way I understood your architecture is doing the same information in different tiers, like Mortar Data, Cassandra, and vertical.
So he asked, in the service architecture and in the storage layers under the service architecture, are we storing different information? And the answer is yes. Mongo, we find, is much better at storing aggregates or counts. The incrementers are faster and way more reliable than counters in Cassandra. We try to avoid them. We can't really, but we use Mongo, for instance, for handling our users and our accounts because it's got a great object layer, an ORM layer that Rails plugs in very easily with. So it's just different. There are different types of data, but we also use the same type of data for guaranteeing accuracy.
My question was like, if it's doing the same data, do you have processes to reconcile the differences?
Yes, we do have processes to reconcile the differences. At the end of every hour, at the top of every hour, we try to make everything within our system trigger-based. So every time a new event comes in or a new message is created, that will kick off n number of other events. But there's just certain things that it really won't work with. So at the top of every hour, we have cron, kick off a couple of jobs that say, hey, reconcile the data between Cassandra and Vertica. Or, we have a bunch of processes that do that, but that's a pretty typical one.
How do you know when those URLs that you're pulling your ingest from go down or not accessible?
So the question was, how do we know that the URLs? Yeah. Actually, we don't. So the question was, how do we know that a URL is becoming accessible? Actually, we don't really care. All we care is we want to know how many events that we've seen for this to date. If it doesn't exist anymore, it's kind of not our problem. It's one of those things that it would be nice for us to know, but then we'd have to build a crawler, and that's not really the business we want to be in. I got time for one more question. So the question is, how do we reconcile data? So we do have what we call an authoritative data store, which is what we use Cassandra for. Cassandra is the authority. So if any one of the data stores says something else, we say, set it to what Cassandra says, and if you don't like it, too bad. Thank you very much. If you have any questions, I'll stick around and hopefully be able to answer them later.